of people that have, like me.
It's a lifestyle choice.
Okay, so today we're going to move from looking at the terminating case for analysis to the steady state case. As we've seen, the difference between a terminating case and the steady state case is that the terminating case has a natural ending condition, whereas steady state is about a system that basically fluctuates about the same, well, state. The thing to understand is that a dynamic stochastic system in steady state is typically not constant. In fact, if it's stochastic and dynamic, then it isn't constant. So even a measure that you're looking at, as we will see, does not stay fixed, but will typically fluctuate about some steady state value. And what we're interested in moving from the terminating case to the steady state case, is we're interested in finding out what that measure is, or those measures are. Now, another difference is that in the terminating case, the initial conditions affect your answer. So in our canonical multiple server queue example, the fact that we start the system empty will affect what our measure is. So if we're only running for, say, a day's worth of activity, if we start empty versus, let's say, if we started with 50 customers in the system to begin with, you're going to get a different answer. In steady state, that's not true. In steady state, the initial conditions are irrelevant. And in fact, if the initial conditions are affecting the answer, then you're not in steady state. Again, the term is a little bit of a misnomer unless you really kind of understand what's going on. The steadiness is the fact that there's some steady state probability distribution that is going on. And it is typically a very complex one because it isn't just a single probability distribution, it's actually a stochastic process. Now, have you have encountered stochastic processes before, right? Have you seen Markov chains? Do you know what a Markov?
Yes.
Yes, some no. Everybody? No? Okay.
They don't teach that here.
They don't?
Markov chains, not for the ones we took.
Oh my God. Well, they should.
It's like it's raining today, what's the chance it's gonna rain tomorrow?
We could cut SimKit and do like a class of Markov change.
Or we could just tack on Markov chains to
Or we could
SimKit.
just do none of it.
Yeah. Yes, we could. But it would be wrong.
Different people have different values of wrong.
Well, what in Markov chain, for those of you who know Markov chains, what is one of the things that they ask of a Markov chain?
The current state, how it affects the next state.
Okay, that's one of the things that defines it, these transition probabilities. So given the transition probabilities, what kinds of questions do you start asking about that Markov chain?
If it rained this week, what's the probability it'll rain next week?
Okay, and what else?
And
Did they ever find the steady state probability distribution?
I don't know.
No. Well, it turns out that if you solve a matrix equation, then you can determine the steady state probability distribution of a Markov chain by certain manipulations of the state transition matrix. And for those of you who have not encountered Markov chains, then that if you have, that would be a nice way to connect what we're doing here with what that is. Because with a Markov chain, yes, one of the transition probabilities say what, given today's state, what is the probability of the next state? And because those are conditional probabilities, that means that they're not independent. And that's the case here. As we have seen, demonstrated, the data coming out of a simulation, of this kind of simulation, the data are typically correlated, sometimes very highly correlated. And what that means is that the implication of that is that you cannot use the raw data to form your confidence interval. And in the terminating case, there were two reasons for that. The first was that the observations were not identically distributed. And the second was that they were autocorrelated. Now, in steady state, actually the first part becomes true. In other words, if you have a simulation, or any system for that matter, in steady state, then the probability distribution of each observation is identical from one to the next. To make it specific, if we're looking at, say, the steady state time in the system for our multiple server queue, in steady state, each customer has the same probability distribution for that time in the system. But what makes it still not possible to use the raw data to compute a confidence interval is that they are still autocorrelated. So those are the two issues of dealing with data in steady state. Well, the first is, when are you in steady state? Given that with almost certain probability, you are not starting in steady state. And then the second is that once you even reach steady state, the data are still correlated. So how do we deal with that? There are actually a lot of different ways of dealing with that, but there's really only one way to deal with the initialization bias, and that is to warm up the system, that is, to run it long enough so that you're reasonably sure that it's in steady state. And unfortunately, we don't have time to kind of go, all of the methods that are possible at this level are basically more or less ad hoc, and so that's the approach that we're going to take. And once we reach steady state, though, again, because the data are still correlated, what we're going to do, at least the first approach we're going to look at, is what's called replication deletion. So the deletion part has to do with the fact that we're going to delete the observations prior to steady state, and the replication is the fact that we're going to do this again and again, as we did in the terminating case. So our initial conditions are not typical of steady state. If we wanted, we could actually start in steady state. If we knew what the steady state probability distribution was, then we could conduct the following experiment. We could generate our initial conditions from that steady state distribution and then continue from there. And there, in that case, we would actually start off in steady state. There's only one problem with that. Well, the practical problem is we don't know what the steady state probability distribution is. In fact, we're even doing everything we're doing here, we're not going to find the steady state probability distribution. We're actually just going to find a reasonable estimate of the steady state mean, which is not the whole distribution. So there's a big difference between finding just one parameter of a distribution and finding the whole distribution. The second is just, if we knew what the steady state distribution was, then we would not have to conduct the simulation at all because we'd have everything that we needed. Our steady state measures may be very different from the initial observations, and in fact, the initial observations are typically biased with respect to the steady state measure. So now, are you familiar with the statistical meaning of bias?
Vaguely. Our statistics classes are basically just like Target call, plug this into Excel, see what pops out. So
Oh, geez, so the feel method of statistics. Okay, well, with a word like bias, does that sound like it's a good thing? No. Okay, so what is bias? The statistical meaning of bias is that if we are trying to estimate a particular measure, in this case the mean, but it could apply to any measure, bias is that in this case applied to the mean, that our estimate of the measure is not the expected value of our estimate is different than the measure we're trying to estimate. In other words, if I'm flipping a coin and trying to find the probability of heads, and my rule is that every other time it comes up heads, I'm just going to ignore it and not count it, then is that going to produce an accurate estimate of the value of the probability of heads? No. Why? It's obviously biased. So, I mean, bias is a bad word, so bias is bad. So here's what initialization bias looks like, just sort of in the abstract, and we'll see that this is. So here's the measure we're trying to estimate. And again, moving from the terminating case, where each observation has a different mean, to the steady state case, where there's only one single mean in steady state, if there is one. I mean, in some cases there isn't one, it just blows up, but we're going to assume that there is one. So that's just one single number we're trying to estimate, and here it is. Now what the blue line is this is the actual, no kidding, real mean of the successive observations. Again, this is an abstraction, but in other words, these are not the observations. This is the actual, no kidding, mean over, for each customer T, for T, the first customer, second customer, etc. So this is the value we want to estimate, and these are the values that we're getting. So if I use these, let's say I run my simulation up to here, and this is the mean of the data that I'm gathering. This is the true but unknown mean that I'm trying to estimate. So is it clear that if I use the data here, that I'm not going to get a very good estimate? Yeah, so in other words, if I use this data, then I'm going to get some value, and maybe the mean is right here. So this is going to be my mu hat. See, statistics is easy. You just take a variable and you put a hat on it, right? So this is the value that I'm going to report, but this is the true value. And notice I'm off by a lot. Now, how much you're going to be off by? Well, the thing is, you never really completely know. But if I want to get a more accurate estimate in general, what's my typical strategy? Get more samples, right. And what does more samples do? It gives you a more and more accurate estimate of what I'm trying to do. So if I'm using these data here, and I take more and more samples, and I get a more and more accurate estimate of the wrong thing. And this is that's a pretty big difference. In other words, these data down here in the initial part are biased, and bias is bad. And my usual tactic of getting a more accurate estimate is just going to get me a more and more accurate estimate of the wrong thing. So if I'm doing this, I can report a really nice tight confidence interval of the wrong value. So is it clear that's not a good thing? Yeah, so, okay. So if I knew that this was what was going on, then basically, depending on what my tolerance was, because you never do truly reach steady state, but if ideally what I would want to do is throw away all of these data here and then just start collecting right here. And that's the truncation part. In other words, the truncation part is I'm going to, and the term is to warm up the simulation. And, well, it's in the old days, and you can ask your grandparents about this, they used to have these hi-fi systems, and you'd turn them on, and you'd hear a boom. That was basically the initial transient of that electronic system. So a lot of this is by, all dynamic systems have this characteristic. And so basically, the hi-fi was reaching steady state because it was starting with sort of nothing going on. Then when you turned it on, then the circuits were reaching a certain steady state. And then as you applied different, different fluctuations to the voltage, then it would turn it into sound, et cetera, et cetera. But that initial boom was the initial transient of a system. So when you look at when you study those kinds of systems, you find the same type of thing. Now in the simulation, this initial transient is like that initial boom. Okay, so the initial observations are biased. That's bad. We warm up the simulation, we run it for a while, and then we want to clear the statistics and then carry on. So if we have tally data, and our truncation point, what I'll call T, is going to be how many customers we will observe before we say we're in steady state. And then because the observations are autocorrelated, again, we cannot just use the basic ones, but as with the truncating case, what we can do is we can run it for a while and then take a mean of that, which is what we're doing here. So we're going from the truncation point, the first observation after the truncation point, n more observations, and then finding the mean of that. The other thing that this does, and there's a more advanced central limit theorem that applies to autocorrelated data, which under mild assumptions says that actually the averages of things becomes asymptotically normal, even if it's autocorrelated. So the other advantage of this is that even though the underlying data are typically not normally distributed, the averages of them by this central limit theorem converge to the actual one. Now, for time-varying data, we have a similar issue, except we have to deal with the areas under the curve. So for time-varying data, again, our truncation point T is a time. So here is, for tally data, it's an observation. For time-varying data, it would be a time. And there again, Well, if it isn't clear that the tally data, such as the delay in the queue or the time in the system, are not correlated, when it comes to the area under the curve, it should be clear that there's sort of massive correlation, right? Because, you know, if I have, so if I'm looking at something like this, so what's the correlation between the area at this time and the area at this time? Well, they both have the same area in common, so there's going to be a lot of overlap. So depending on whether our measure is time varying or tally, we're going to truncate at an observation or at a time. Now, if we're doing this for multiple observations that are both tally and time varying, then we would want to truncate at a particular simulation time rather than a count. And there, it's the notation is more complicated than it basically is that we choose a truncation point, and then after that truncation point, we simply start taking the tally observations as well as the time varying observations. Okay, so again, in our steady state measure for the mean, unlike the terminating case, it is a single value. If we're in steady state, the data are basically identically distributed, and that they at least have the same mean. So if I have observations that are identically distributed, they do still have the same mean if they have a mean. Again, but most of the data that most of the distributions, even the unknown distributions that we have, do have a mean. Mathematically, you can construct distributions that don't have means. But the problem is that the usual estimate of the variance is biased. So if we try to apply that formula, I mean, here's the danger of sort of the software-based statistics. If I have a bunch of data, I can always plug it into the formulas. I can always sort of stick it into my software and say, give me the mean, give me the standard deviation. You have a bunch of numbers, you can always compute that. The question, though, is, are they biased or not? Now, if we are in steady state, then our estimate of the mean is actually unbiased. You can show that. But the estimate of the variance is typically biased. And when we are dealing with positively correlated observations, as we typically are, as we've seen, the bias of the estimate of the variance is in the wrong way. In other words, think of what is it the variance is measuring? Yeah, but I mean, more just in general, variance is measuring the variability of my observations. In other words, if I take one observation, if I have a high variance situation, then my next observation could be way, way different. Again, sort of think of the difference between, think of our bell-shaped curve, and so think of the difference between a normal distribution that looks like this and a normal distribution that looks like this. They could both have exactly the same mean, but this has a much smaller variance. So if I'm taking observations from this distribution, they're all going to be clustered around the mean. Whereas if I take observations from this distribution, even though they're going to be clustered around the mean, they're going to be spread out much, much more. And the variance is an estimate of how much they get spread out. The problem with our estimate of the variance in the case of positive correlation is that we think our distribution looks something like this, whereas in fact it looks something like this. In other words, we are way, way overconfident. The half interval of our confidence interval is much, much smaller than it has any right to be. So if we are dealing with biased variance, and the bias in the variance comes from the fact that our random sample is not a random sample. Remember the definition of a random sample: independent, identically distributed. In the case of in the case of the terminating case, where we're dealing with the initial part, both the i's are wrong. We are not independent and we are not identically distributed. In the case of steady state, though, we get the second I. We are identically distributed, but we're not independent. So the thing is that we're way overconfident. And again, it's like if we think we're really, really tight, if we think that we're coming from a very tight distribution like this with a small variance, whereas in fact we're dealing with a very large variance, then what the problem is that we could be way off in our estimate and not know it. Okay, so that leads to the replication deletion method. And the idea is that we take one observation and, so let's say it looks something like this. So here we're starting at time 0. And what we do is we do some preliminary analysis to determine what our truncation point is. So let's say, and how do we do that? Again, like there are some heavy-duty mathematical ways of looking at it that we don't have time to get into. In practice, what you can do is, and we'll do this in a second or two, we can just sort of look at the observations and sort of see where it looks like they kind of flatten out. So what we're going to do is we run the simulation. Then what we're going to do is throw away all this stuff here, run it for a bunch more, and that gives us our first observation. And it's going to be a mean, and that's going to be 1. And then we're going to do it again and again and again. Just as in the terminating case, when we do it again without restarting our virtual machine, then our random number generator picks up where it left off. And so the next replication is going to be independent. And because if we follow the same protocol each time, that is, we are going to truncate it, we're going to truncate at the same place and run for under the same rules. So it could be a number of observations or a particular time, whatever it is. We're running a second experiment under identical conditions, and so we will get a second observation, which is now independent and identically distributed from the first. If we are indeed in steady state, and we'll never know for sure whether we are, but if we are indeed in steady state, then this is going to be an unbiased estimate of the mean. If we are performing independent replications, which we will be, limited only to the extent to which our random number generator is truly independent, then we will be having independent, identically distributed observations. And to the extent that we've actually reached steady state and our mean is of each replication is actually in steady state, then we now have independent, identically distributed observations where the expected value of our observations is the thing we're trying to estimate. So these means are unbiased to the extent that we're in steady state. And the variance of these, now, this is not the variance of our system, this is the variance of these observations, but that variance is unbiased too, because if we are independent. So this is what we need to do in steady state. So doing this piece is fairly straightforward, especially if we have objects that will kind of do it for us once we tell them the right information. The trickiest part is, bless you, is figuring out where to truncate. Just to, again, and a lot of this was kind of abstract, so let's try to make it a little more concrete. So we're going to go back to our multiple server queue and just run it a whole bunch of times. Now the thing is that these are very, the variance on these can be very, very large, and so each individual replication fluctuates wildly. So what I have here is I have the, remember there are entity server, so the entity arrival process, we have the entity server, and as before, I'm going to reuse the exponential and the triangle composition that we created. And by we, I mean me, of course. So I have, there's another one, and again, this is, if you pull, this is all in there. So I just kind of threw together, just for this particular case, I just threw together a little guy who's going to listen for these things, but keep track of the individual observations. So I put them all kind of in a list. And what I want to do is I want to run it for a while. So I want to run it for, in this case, for 15,000 delays in queue. Actually, no, I'm looking at the time in the system for here. Just, well, here, let me just show you what some of the issues. So supposing I only want to run it for 100. So how do I do that? Well, I say I want to have this many end service events. So the end service events is where I get the time in the system. And it has an argument that's an entity. So I just say I'm going to stop on this many events, and that will give me exactly, in this case, what if I want to run it for 100? So let's, so I'm going to run it 500 times for 100 service completions. And write the whole thing to a file. I'll call it time in system. So when I run that, and I ran it for 500 replications just to kind of smooth it out, because of in just playing around with it, it was very okay. So I'm going to stick this in R. Okay. Okay, so here's what that looks like. For some reason, when I'm hooked, when I do this and I'm not hooked up to the monitor, it comes out nice and big. But okay, so now look at this. These are the successive times in the system for the first 100. Now, if you look at this, how confident are you that this has reached steady state? You shouldn't be, because what is this going to do after that 100th guy? Is it going to flatten out, or is it going to just keep going up? We don't know.
Yeah.
So let's see, where is it? Okay, so what was I actually? Well, just to, let's see, was it here? If you remember, we took the same system, using the same observations, and then when we ran it in the terminating case, let's just look at the time in the system. Our confidence interval for the terminating time in the system was 17 something. And the half-width was like 2.4 with this for 30 replications. And for that, again, like, well, what if we wanted a tighter confidence interval? Well, you run it for a bunch more replications. So if I want a tighter confidence interval, I'd run it for 100 replications. And now it's around 16 with a plus or minus 1.3, and that all includes the 17. Just so remember, the confidence interval says your true but unknown mean could be anywhere in here. And I'm confident about that, and you all know, they at least told you the frequentest interpretation of confidence interval, which is that if I were to perform the same experiment again and again, and here I have a 95% confidence interval. If I were to perform this experiment 100 times under exactly the same conditions, then actually 5 out of those 100 on average would not include the mean. In other words, I would miss the mean 5% of the time, which led a friend of mine to quip that statisticians are the only people he knows who insist on being wrong 20% of the time, or 5% of the time, whatever it is, 1 time out of 20. Okay, so our terminating case, our time in the system looked to be about 16. For this, oops. Damn it. Okay, so in this, it's actually looking to be about, it was kind of peaking up around 18 there and didn't show any signs of letting up. So if let me show you what happened when I, oops, that was that. Okay, so this, in this system, as it turns out, looking only at the initial part was just very, very misleading if we were interested in the steady state. In other words, what was happening in this particular case, as we will see, is that we were kind of cutting off the system way before it reached steady state. Steady state was very, very different from what we were observing. Let's see. Just sort of plot that and see. Okay, so here's, if I ran it for 15,000 of the guys, then this is what it looks like. And you can't really see it, but that's a, well, let's see. The mean, well, the mean of the whole thing is actually around 47. But as we can see here, and again, each of these is the average of about 500 replications. So this when you don't smooth it out, when you don't kind of do that, it just kind of goes wild, and it's hard to tell what's going on. Clearly, or I mean, it should seem sort of clear that around here it starts to fluctuate. In other words, it should be clear that here it's not anywhere near steady state. But once it starts really kind of fluctuating around a particular value, then we can see that it's actually, we could make a good guess that this is where steady state is. And so our truncation point would probably, if we want to be reasonably accurate, could be anywhere between here, this point here, and anywhere here. So really, the most reliable way, not reliable, the easiest way to try to see whether you're in steady state is to do something like this, sort of plot it out and see where it starts to fluctuate. And you can actually do this with fewer replications. It gets a lot noisier. The fluctuations become very, very strong, whereas here it should be fairly clear. Okay, so those are the issues around steady state. Again, to recap, there are two issues. One is initialization bias, and that should be clear between the abstract diagram, as it were, and what we see, at least for this particular measure. Now, not every measure looks like this, but this is fairly typical. So the point is that this kind of abstract representation is actually a fairly typical one. It should be sort of clear that if we were to if we knew the actual, no kidding, distribution of this, of what the mean is, it would kind of look like that. That should be fairly clear. So again, initialization bias means that we need to truncate. Autocorrelation means that we can't just take the raw observations, because autocorrelation screws up the estimate of the variance. Autocorrelation does not bias the estimate of the mean if we're in steady state. So our estimate of the mean is biased here, but probably unbiased over here. So the mean is okay, but the variance is still screwy. So to reach steady state, we truncate. So you see, this is one of, we go to the doctor and what's the problem? It hurts when I go like that. Well, don't go like that. These observations hurt because they produce bias. And even if we include them, this is contaminated data. This is contaminating we're trying to find what this mean is here. And these are giving us the wrong values. So we want to get rid of those. And then once we get rid of it, we run it for a while, and then just do the whole thing over and over again. And I'm sure you're all wondering, well, how do I do that? Well, you'll have to tune in next time.